Hey everybody. So this particular video is probably going to be pretty long. You can see by the number of learning objectives that there's a lot to it. I'm kind of ambivalent about it as a procedure. It's a really useful. I'm going to teach you a really useful procedure called completing the square. But it's important for you to know that why I'm doing this. Essentially, as far as solving quadratics, lesson 1D gives you everything you need numerically, but essentially using the quadratic formula. You might wonder where the quadratic formula came from, and that's what we're going into today. But essentially, everything I'm going to teach you in this can be done using the quadratic formula. And so one question you might ask me is, why are we going to spend time learning this procedure if we already know how to do the same thing, essentially by throwing it into a formula and getting the answer? And the answer has to do, the reason I want to deal with this in this particular class, and the reason I think this is important is for a few reasons. One of them is that it's important that you know where things come from. Essentially, this is a university level math class. Nothing's magic. Everything comes from somewhere, and there's always a trick or a reason or a justification. And you now, as an adult, have it within you to learn all those tricks and justifications and to understand the reason for everything. Not just in math, in everything in life from this moment on, there's nothing that you can't understand. There's nothing that somebody else understands that you can't understand. There's no justification that came out of nowhere. Everything's for a reason, and you have the capacity to understand. So don't take no for an answer. So part of it is that I want you to see where this stuff comes from. Another reason is that it involves a lot of really useful algebraic steps, where these algebraic steps kind of rely on a really good understanding of algebra, a really good understanding of how to use equations and square roots and things like that. And so it's a really good test at this point in the game to see how much you understand, how concrete your understanding is of the mathematics you learned essentially before taking this class. So using this as a testable topic, essentially teaching you this and asking you to be able to write exams where you have to repeat this type of the contents of this lecture, it's kind of about, it's a diagnostic tool for me to see how much you understand, and more specifically to recognize if there are some aspects of your understanding that you're kind of missing. It should be within you entirely possible to understand each and every step that we do in this. Everything should make sense. There's a lot of bricks to this particular building, so please be patient with it. But you deserve to know where these things come from, and also this is a great opportunity to see if you need work on anything, where fixing it up right now at the start of the term will save us a lot of time. So essentially that's why we're doing completing the square, even though this is a procedure that we could do already using the quadratic formula, because the quadratic formula just cuts to the end of completing the square. Okay, so in this video you're going to learn the problem. I want you to explain the problem with simplifying radicals to me. This is a thing from pre-calculus. This is like grade 9 or 10 math. But you need to understand this, and it's really important that you understand it because this shows up a lot in Math 100 and Math 101. A lot. I'd say that maybe 30% of the final exams that I mark in Math 101, they get 10% of the test wrong because they're still making this mistake. So it's really important that you understand the issue with simplifying using square roots, and that idea is really concrete in you, because it's going to come up over and over and over the course of your mathematical education, and I don't want you to lose those marks. So if we set everything straight right now at the very start of pre-calculus, you should be fine. You're going to explain what a perfect square quadratic polynomial is. Perfect square quadratic polynomial. Maybe you should have a bigger line here. Like perfect square quadratic polynomial. You need to understand what a perfect square quadratic polynomial it is. It's a certain type, it's a special type of quadratic polynomial, just like how you're a special type of person. Yeah, so it's like that. You're perfect. It's perfect. It's a perfect square. Okay, so then you need to recognize a perfect square, factor a perfect square. We'll talk about those. Take the root of a perfect square, and then use the complete the square. The algorithm's called complete the square. If you didn't recognize the title, to solve quadratic equations. We're essentially going into in lesson 1.d. I said, you know, it's really tricky algebraically to solve a quadratic equation, and it is. There's a method, though. They figured out a method. It's really weird. It's called completing the square, and I want you to learn how to do it. And then I want you to explain the word derivation. We're going to learn about derivations today because I want you to be able to derive the quadratic formula. So, let's begin. The quadratic formula is all about roots. Somebody gives you a quadratic polynomial, and they say, find the roots of this quadratic polynomial. Solve this equation. What you're going to do, write it all out, and then you take all these numbers and you plug them into the quadratic formula. Minus b plus or minus square root b squared minus 4ac over 2a. And this has two values, maybe. Sometimes it has one value, sometimes it has no values. It's not going to have four values. So you use this to figure out what the two roots are. Where does this come from? Was it given to us? Did somebody wake up and look at the moon and see this scrawled on the surface of the moon? Did it come from aliens? Where did this equation come from? Well, the answer is what we're going to be talking about today. This equation comes from a procedure called completing the square. That's the name. The name's a bad name, first off. Technically, the name shouldn't be completing the square. It should be called completing the perfect square. There is a type of a quadratic. There is a type of quadratic expression, a quadratic polynomial, called a perfect square. Not all quadratic polynomials are perfect squares, but there's a type of perfect square. And if we study the properties of perfect squares, we can figure out how to harness perfect squares to get this formula and to solve more generic quadratic formulas. Quadratic equations involving quadratics, right? And so we can use this procedure called completing this perfect square, not just for finding roots, but also, you know, if somebody gives us plus 3x minus 2 is equal to 17, we can manipulate this directly using only algebraic steps and complete the perfect square procedure to figure out what the solution is. Okay, so that's the introduction. It's only 17 minutes long. Perfect square. A perfect square polynomial. Alright, so your generic quadratic formula looks like this. Ax squared plus bx plus c. Sometimes there are some quadratics that you can factor and some that you can't. But of all of them, there are some very special ones that you can factor in the following way. Call them px for perfect. Factor. Sometimes you can factor them, sometimes you can't, but there are some that factor. When you factor them, they factor just like this. Ax plus b all squared. It's not two different linear terms multiplied together. It's a single linear term, all inside parentheses, all to the power 2, with nothing else beside it. Just this one element. That's what makes it perfect. Not every expression is a perfect. Not every quadratic expression is a perfect square. In fact, most of them aren't. So how can you tell if something is a perfect square? How can you tell if it is a perfect square? Question mark. I mean, so for example, if you came up to me in the hallway and you were like, "Hey, Dr. Tippett," and I said, "Well, thank you for remembering my honorific," and you said, "Yes, is this a perfect square?" I'd say, "Whoa, I don't know." How does one go about telling if something's a perfect square? Well, the deal here is that we can do a little bit of reasoning, and I'm going to spell out the reasoning for you. Let's take a quick step back here. I want you to think about how many free numbers there are in a quadratic expression. By free numbers, I mean, how many numbers does somebody need to give you to define a quadratic expression? The answer is 3, right? They need to tell you what this number is, and they need to tell you what this number is, and they need to tell you what that number is, and if they've told you all 3, you've got your quadratic, right? So for this one, it's 4, 2, and 10. How many free numbers do you need to describe a perfect square? There's only 2 of them, right? So somehow you only get 2 free numbers, 2 free coefficients when you're defining a perfect square, whereas more general quadratics, you get 3 numbers. And what that means is that in a perfect square, if somebody gives me an expression like this and they ask me if there's a perfect square, there should be a relationship between these 3 numbers that there isn't usually. Okay? I'm going to elaborate that same point in a slightly different way. Let's take this perfect square and we'll expand it out. I'm going to multiply it out. ax plus b times ax plus b. Multiply this out. Ax times ax plus b times ax plus b. And this becomes ax times ax plus ax times b plus b times ax plus b squared, which becomes a squared x squared plus 2abx plus b squared. Okay? So generally speaking, for something to be a perfect square, this number and this number and this number have to all be related. How do you figure out that relationship in order to test? What you do is, first you get that number. That's the coefficient there. I'm going to say a squared is equal to 4, so a must be equal to 2. Now, I'm going to take this second number. That's, in this case, 2. So 2ab is equal to 2. I'm going to plug this in to there. So that's 2 times 2b is equal to 2. So that's b is equal to 1/2. And then the last term here has to be b squared. So b squared is equal to 0.25. And then I compare this number to that number. See? And if they agree, then this is a perfect square. But they don't agree. So this one's not a perfect square. I'm going to re-explain that in more detail as a procedure you can use to test. But overall, I want you to understand the point here. The point here is that if your polynomial is a perfect square, then these three numbers can't just be any number. There's got to be a relationship between them. And that means that if I know one number and I know the second number, I can predict what the third number is going to be. Okay. So, let's try this. I'm going to try it again on a different example, and then I'm going to spell it out a little bit more for you. So first I'm going to write out my expanded perfect square. Perfect square. A squared x plus 2ab x, it's supposed to be squared, plus b squared. Somebody gives me a formula. So they go, here is a formula. 3x squared plus square root 84 times x plus 7. And I say, oh, that's very strange. And they ask me, is this a perfect square? How do I figure out whether it's a perfect square? The principle here is that if it were a square, there would be a pattern, a relationship between these three numbers. So what I need to do is I need to figure out if that relationship holds. What's the relationship here? I mean, it's just essentially saying, take this number, take its square root. That gives you a. Divide this number by a. That gives you 2b. Divide it by 2. That gives you b. Square that number, should give you that. All right? There's a relationship between all three coefficients if it is a perfect square, and we're using the test to see if these three numbers satisfy that relationship. And we can use our calculators if we want. Okay. So first you take the first coefficient, 3. We'll call that a squared. Now we want to find a. So we're going to take the square root of that expression. Square root of 3. Now I want to figure out what b is. So I'm going to use the second term, this one, to figure out what b is. b is going to be the second term divided by 2 times a. So that's square root 84 divided by 2 times square root 3. Well, that's a weird number. Let me put it in my calculator, see if I get anything. 84 divided by 2 divided by square root of 3. Oh, weird. I get 2.645751311 question mark question mark. Okay. So what we're going to do is now that we found b, supposedly, we want to see if this last term is equal to b squared. So I'm going to square this value. Oh, and I got 7. So yes, this is a perfect square. And the neat thing about knowing that something's a perfect square is that you can write it in its factored form really easily, right? Because you know that the factored form is just going to be ax plus b. So in this case, the factored form of this is going to be square root 3, that's a, times x plus, I guess b is the square root of 7. So this one is a, and this one is b. All right. So I recognize that what I've just told you is a lot. Let's keep things straightforward. Can you use the test? How do you use the test? The test is just us writing this thing out, using this term to find the value of a, using this term to find the value of b. It's a test, mind you. I'm testing to see if these three numbers satisfy a relationship. And then I make a prediction for what this third number needs to be, and I compare it. And if those numbers match, then it means that this thing is a perfect square, and if they don't match, it's not a perfect square. So let's try an example. Try this yourself. I'm going to show you how to do it, but I want you to try it. Find the perfect squares and factor them. So here are our four equations. Here's f of x is equal to x squared plus 2x plus 4. G of x is x squared plus 2x plus 2. H of x is equal to x squared plus 2x plus 1. S of x is equal to 2 minus 4x plus 4. Just because the last example had really weird numbers in it doesn't mean that they all need to. In fact, for this course, I mean, you need to know the general procedures and the general arguments, but generally speaking, for this course, I'm usually going to try to have pretty nice round answers. So we're going to see lots of 1s and 2s and 3s. All right, so I want you to test to see if something's a perfect square, and if it is, factor it. To do this test, let's start by writing out what a perfect square looks like. It looks like ax plus b squared, and if you expand this out, it's a squared x squared plus 2ab x plus b squared. So we're looking for a relationship between the coefficients. Let me give myself some room here. Down here. All right. So let's start by defining what a is. A is the square root of the first coefficient. That's going to be 1. So b is going to be this coefficient, 2 divided by that coefficient times 2. So now b squared, hold on, you know what? I'm going to do this in 2 steps just so you don't think I'm bonkers. Divided by 2a. So this is going to be 2 divided by 2 times 1, that's equal to 1. And then I find b squared, which is equal to 1, and I'm going to compare with this number. Hey, this number doesn't agree with that number, so it's not a perfect square. Let's try this one. Let's do it as a different color. Put green. A squared is equal to 1, so a is equal to 1. B is equal to 2 divided by 2 times a, so that's 2 over 2 times 1, 1. So b squared is equal to 1. And now I compare this and that. It's not a perfect square. Okay, I want you to understand that what we're doing here there's a reason for this procedure we're using. All I'm doing is I'm like, these 3 numbers, they're related, right? If I told you what this number was and I told you what this number was, you could figure out what this number here was. Do you see what I'm saying? So this is essentially me saying, do these 3 coefficients have the same relationship as this formula? And if it does, then it means it's a perfect square, and if it doesn't, it says it isn't. Please work through that yourself and make sure you understand what we're talking about. Don't give up. This isn't something you can't understand. This is definitely within your grasp. Let's try this one. A squared is equal to 1, so a is equal to 1. So b is equal to 2 divided by 2 times a, so that's equal to, all right, so the 2, where'd that 2 come from? That 2 is that. Where'd this 2 come from? That's that one. Okay. It's a coincidence that they're both 2. 2 over 2 times 1, so that's 1. B squared should need to be 1, and now I compare. Hey, they match. This number and this number matches. That means it's a perfect square. So I can factor h of x in the following way. It's going to be a, which is 1, times x, plus b, all squared. Right? What about the last one? So a squared is the coefficient in front of here. That's a 1. So a is equal to 1. So b, that minus 4, divided by 2a. Minus 4 divided by 2 So that's minus 2. So b squared should have to be equal to 4. And now I compare. Hey, yeah, they're the same. It's a match. And that means that we can rewrite this. It's a perfect square. It's 1 times x plus minus 2 all squared. And if you like making this thing fancy, you can write it like that. Okay. So that is all you need to know about figuring out why, if something is a perfect square. Perfect squares are useful for a variety of reasons. One is that they're really easy to factor. So if you know something's a perfect square, you just figure out what little a is, little b is, and then throw it together. But there's more to it. I mean, there isn't more to it than that. That's all there is to testing to see if something's a perfect square. But why do we even care about perfect squares? It has to do with radicals. Radical's not really a word I used very much. It's something. It's a word I really learned teaching math rather than using math. But a radical is an expression that's under a square root sign, like that. Okay. So people like simplifying radicals. People want to simplify. They want to simplify radicals. This is generally true when it comes to world politics, but it's definitely true when it comes to mathematics. It's something people want to do, but some radicals don't lend themselves to simplification. There's no simplifying this expression. That's it. That's all you got. You can't break it up. You can't do anything with it. And there is. I want you to copy out the following thing just as I do it. So you'll have to pause the video to copy it on a sheet. First, write this: x plus 2, and then write this: square root x plus square root 2. Okay. And then get out your red pen and make it a big one. And then draw a big X through it. And then draw your mother's face looking disappointed at you. That's a pretty good likeness. Hey Mom, how's it going? It's a neat haircut. And she will say, do not do this. This is literally the thing that people, it's a mistake that people in calculus, in Math 100 and Math 101 do all the time, and it's entirely wrong. Don't do it. It doesn't work. That type of breakdown works for some functions and some expressions. Right? So for instance, ooh, that's too big. So for instance, like 3 plus 2 can be written as 3 plus 2 without the parentheses there. Square root signs don't work like that. And the easiest way for me to explain how they don't is with an example. Okay, so what's the square root of 36? It's equal to, wait, hold on, not 36, sorry. What's the square root of 16? It's 4. And what's the square root of 9? It's equal to 3. So what's the square root of 16 plus 9? Now, if you hadn't been yelled at just now, you probably would have said, well, it's going to be 4, or wait, hold on, it's going to be 16 plus 9, 4 plus 3, it's 7, right? But lucky for you, your mom came in and yelled at you for it. So, hold on. Let's be able to see some of it. Because there's another way to evaluate this expression, and that's just to add the two numbers together. 25. What's the square root of 5? 25. It's 5. Five, not 7. They're not the same number. If this was a legal step, if it was something you were allowed to do with the laws of algebra, then these two numbers would be the same. But they're not the same, and that's because it's an illegal step. Do not do it. Definitely don't do it. Like draw Godzilla on the side of your notes, blowing fire at it. Here's Godzilla. He's here to help us. He is blowing fire at this particular set of things because it's so wrong. Don't do it. Just cement in your brain that that is an illegal step. That's literally falling off a cliff. If I can get you to understand that, everything I'm about to tell you about completing the square is going to make a lot more sense. But it's something that you should have been warned against a lot over the mathematical education. And nobody remembers how to do it. I mark a lot of Math 100 and 101, and I think I marked a Physics 301 test where they made the mistake. It's super wrong. Don't do it. It's just giving you're taking marks and putting them in the garbage. So the long and the short is just respect the fact that you ordinarily can't simplify radicals. Okay? So everything I'm about to tell you is built on this premise that most radicals, you can't simplify them at all. Okay? So burn that lesson into your heart because we're moving on. So, quadratic. Oh wait, hold on. Roots. What's the point to a square root? The point to a square root is it inverts the squaring of a number, right? So my favorite way to write it is in terms of exponents and exponent algebra, which if you need a review of, there's a nice review in the textbook in chapter 3. But essentially, the deal is that square rooting and squaring a number are opposite effects. So if I square a number, I can take the square root of that object to get back the original number. Okay, they're called inverse relationships, inverse operations. Okay. So like I said before, roots work for a variety of things that are squared, right? So if I square x, you can write it as x squared all to the 1/2. That becomes x2 times 1/2. That becomes x2 over 2. That becomes x to the 1, which becomes x. So you can use the square root sign to simplify things that have squares on them. I mentioned earlier that there was no that algebraically manipulating quadratic formulas to try to solve quadratic formulas. If you have an equation with a quadratic on one side, solving for x is really difficult. If you wanted to solve for the value of x, you would somehow need to get rid of the x squared term, right? So as an aside, x squared is equal to 25. You can solve that by taking the square root of both sides. And this gives you x is equal to plus or minus 5, and then you recognize from that that the answers can be x is equal to plus 5 and x is equal to minus 5, right? I mean, that's just basic square roots, basic roots in algebra. So you would use square roots to get rid of the exponent 2 there. You would use square roots of procedure, but often there's kind of not much you can do, right? Like, let me elaborate. Suppose your formula looked like this. You wanted to figure out what the value of x was, so let's take the square root of both sides. The deal here, the issue here, the reason it's tricky is because this expression is a radical that can't be simplified anymore. You can't do it. The one thing you're definitely not allowed to do is rewrite this as x squared plus x to the 3 is equal to square root 7. You're not allowed to do this. Remember? Mom, Godzilla? You're totally not allowed to do it. So because you're not allowed to split up the square root sign between the different elements inside of it, there's no simplifying it. And so as a result, this whole procedure, it's not quite clear how to use the square root sign to isolate x. And generally speaking, that's true. If somebody gives me plus 3x minus 2. If somebody gives me a quadratic formula and takes the square root, there's nothing I can do. Say that equals 3 and they ask me to solve it. There's nothing I can do to this expression to simplify it. This is a dead end. Okay. Most quadratics do not lend themselves to most quadratic expressions you can't simplify by taking a square root. There's a dead end. You can't do anything to it. But when I say most, I mean most. There's some that you can. So for instance, if I had an expression that was like that, you could rewrite this as x plus 3 all squared to the 1/2 and rewrite this as x plus x plus 3 2 times 1/2, which is x plus 3 to the 1, which is x plus 3. If you take the square root of an expression that has all been squared, you can use that square root to cancel out that square and unlock the thing inside of it. Okay? But generally speaking, quadratic expressions you can't. And this is my way of saying that if a quadratic is a perfect square, you can simplify its radical. Let me put it like this. X squared plus, how about 4x squared plus 9, 6, 12. Suppose somebody gives me this expression. If the polynomial under the square root is a perfect square, there is a method that I can use to simplify it. Watch carefully. Let me start with a test. A squared is equal to 4. A is equal to 2. B is equal to 12 over 2a. So that's 12 divided by 4. That's equal to 3. B squared is equal to 9. Hey, look. This matches this. So it is a perfect square. If something's a perfect square, you can write its factored form really easily. It's ax plus b squared. And now you can use essentially algebra to get rid of the square root sign. Be very careful when you're learning how to do this. It's important that you learn all the steps properly because, like I said, making mistakes with simplifying radicals when you're not actually allowed to is so common. There. If the thing inside the square root is a perfect square, you can simplify its radical. So let me emphasize that again. Let's do a quick exercise before we go on. Which is a perfect square. Can you simplify it? If so, do it. If not, don't. There's two aspects to this, by the way. One of them is recognizing when you're allowed to simplify something. That's as big a part of as doing the procedure itself on the ones you're allowed to. It's like, all right. So how about this? X squared plus 2x plus 1. How about 9x squared plus 1 plus 6x. X squared minus 2x minus 2. And 9x squared plus 18x plus 9. So try this one yourself. Figure out which ones are perfect squares, and if you can, simplify it, and if you can't, don't. So let's see, this first one, a is equal to 1, so b is equal to 2 over 2 times 1, so that's 1. So b squared is equal to 1. It is a perfect square. So you can rewrite it as 1 times x plus 1 all squared, so that's equal to x plus 1 all squared to the 1/2, so that's x plus 1 times 2 times 1/2, so that's x plus 1 to the 1. What about this one? I'll use a different color. A squared is equal to 9, so a is equal to 3. So b is equal to 6 divided by 2 times a. 6 divided by 6, so that's equal to 1. So b squared is equal to 1. Oh wow, this one's a perfect square too. Square root 3x plus 1 all squared, which becomes 3x plus 1 squared to the 1/2, which becomes power 1, which is just 3x plus 1. Next one. Let's see. A is squared is equal to 1, so a is equal to 1. So b is equal to minus 2 divided by 2 times 1, so that's minus 1. So b squared is equal to 1. That's a minus 2. It's not equal to 1. So no, it's not a perfect square. So that expression is as simple as you can make it. Alright, what about the last one? A squared is equal to 9, so a is equal to 3. So b is equal to 18 divided by 2 times 3. So 18 divided by 6 is equal to 3. So b squared is equal to 9. Oh wow, this is also a perfect square. Square root, let's see, it's equal to 3x plus 3 all squared, which ... is equal to 3x plus 3. Okay, so here's the big thing. The big thing is that if something is a perfect square, you can take the square root and then simplify to get rid of the squared term. Why is that useful? Well, let's consider solving some equations. So, let's take a perfect square. 9x squared plus 18x plus 9 is equal to 25. Suppose somebody asked me to solve this particular equation. Now, ordinarily, usually with most quadratics, you can't actually do anything to it, right? You're not able to simplify it. There's no way off the top of our heads that we can get rid of that x squared. But if I know that this expression is a perfect square, and it is a perfect square, because we just saw it, this is a perfect square. If I know that it's a perfect square, I can take the square root of both sides. This is a procedure that usually isn't very helpful. Don't forget to write plus or minus. Anytime you take a square root of a number, don't forget to write plus or minus in front of it. Okay? So this is a procedure that usually isn't very helpful. But if we know that the thing under the square root is a perfect square, you can actually simplify it beyond here. Let's do so. It's 3x plus 3 all squared. You write it in its factored form. And then you cancel out the square root and the square, just like we talked about. It's equal to plus or minus 5. And then we can solve this algebraically. So there are two terms. Oh no, people are commenting on YouTube. Okay, well, I'll deal with that later. Okay, so the plus or minus here, if you want to ask me in class, I'll explain why it needs to be there. But it does. And we interpret it the same way as we did in the quadratic formula. So there's two answers here. One where it's plus 5 over 3, and one where it's minus 3 minus 5 over 3. So this becomes 2 over 3, and this becomes minus 8 over 3. All right. So to overview, this whole procedure isn't possible unless this stuff here is a perfect square. Which is why we never taught it to you, because it doesn't usually work. It works for some very, very special cases, but it doesn't work most cases. To elaborate any more, if this number here was, say, instead of being a 9, if this was an 8, none of the following steps would be possible. It's only because it was a 9, it's a perfect square, that I'm able to do this simplification procedure. Okay. So now you know why we care about perfect squares. And it gets better than that. All of these things I said, it's kind of a side note. So this things, everything out goes back to radicals. This kind of a side note. We want you to understand it, but it's not the complete the square procedure. The complete the square procedure is based on all of these issues that we just talked about. So, let's talk about completing the square. We're going to use perfect squares to solve quadratic equations. Okay. So suppose somebody gives me a quadratic equation, x squared minus 4x plus 2, and they ask me to solve. Figure out which value of x makes f of x equal to minus 1. How am I going to do that? Well, I'll follow the first step that I've been doing. I replace the name with the expression for the function. Alright, so now I'd probably want to take the square root of both sides, just like I did last time. There's two problems with this. Can you see what they are? The first problem is you're not allowed to take the square root of a negative number. The second problem with this is that this expression isn't a perfect square, and so there's no simplifying it beyond this. So instead, I go back to square one. Well, let's see. Follow my steps if you can. The first step I'm going to do is move all the constants to the right hand side. Okay, so I'm going to subtract 2 from both sides. X squared minus 4x plus 0 is equal to minus 3. Okay. Now, this expression here isn't a perfect square. Sorry, it's not. But I can imagine, I can ask myself, what would the constant need to be to be perfect square? In other words, I ask myself, hey, what would need to be inside that little box for this to be a perfect square? That's a question I can answer. I can answer that with my test. A squared is equal to 1, a is equal to 1, b is equal to minus 4 over 2 times a, so that's minus 2. So b squared is equal to 4. You would need to have a 4 inside that hole for this to be a perfect square. Step 3. This is why they call it completing the perfect square. Add this number to both sides. So x squared minus 4x is equal to minus 3. I'm going to add that number I just calculated to both sides. What I've just done is I've put in the last piece for this whole expression to be a perfect square. I've completed the perfect square. I've put in the last piece for it to be a perfect square. And now that it's a perfect square, I can take the square root of both sides. You know what? I'm going to do this in 2 steps. Now I'll say factor the left-hand side. It's a perfect square, so I can factor it. And factoring is not too hard. A is equal to 1, and b is equal to minus 2. All squared is equal to 1. And now I'm going to take the square root of both sides. Square root of x minus 2 all squared is equal to plus, minus, don't forget that, 1, and simplify. So this expression becomes x minus 2. I'm sorry, I skipped some steps. Plus or minus, take the square root of 1, it's 1. And so the answer here, and then I'm just going to solve for x. So it's 2 plus or minus 1. So there should be 2 answers. x is equal to 2 plus 1, x is equal to 2 minus 1, that's equal to 1, that's equal to 3, and we're golden. So if you want, you can plug these numbers back in. Let's see. f of 3 and f of 1. So when x is equal to 3, that's 3 squared minus 4 plus 2. 1 squared minus 4 times 1 plus 2. This thing gives me 9 minus 12 plus 2, which is equal to minus 1. And this is 1 minus 4 plus 2 is equal to minus 1. Both of these are solutions. So the complete the square procedure allows me to solve quadratic formulas without having to rely on the quadratic it allows me to solve quadratic equations without having to rely on quadratic formulas. Okay, so let's try another one. I'm going to follow the same steps. If my polynomial expression is 2x squared plus 4x minus 1, I want to solve for g of x equals 47. How am I going to do it? 2x squared plus 4x minus 1 is equal to 47. So the first step I'm going to do is I'm going to move the constant over to the other side. I'm going to add 1 to both sides. 48. And now I'm going to ask myself, what do I need to put inside this hole for it to be a perfect square? A is equal to square root 2. Okay, so a squared is equal to 2. A is equal to square root 2. B is equal to 4 divided by 2 times a. So it's 4 divided by 2 times square root 2. So it's 2 over square root 2. You can write that out as a decimal if you want. B squared is equal to 2 over square root 2 all squared. So that's 4 over 2. So that's 2. So this number here would have to be 2 to make it a perfect square. So I'm going to add that number to both sides. 2x squared plus 4x plus 2. Make sure to add it to both sides. You don't want to break equality here. So this becomes 50. Okay, so now I want to factor it. So this becomes square root 2 times x, and b is equal to plus 2 over square root 2 all squared is equal to 50. Now I'll take the square root of both sides. So this becomes square root 2x plus 2 over square root 2 is equal to plus or minus square root 50. This might be one that we have to rely on our calculators a little bit more for, but that's okay. And also, I want you to know that there are some simplifications that I could make. I could simplify these square roots a little bit more. Also, I could have divided this original thing by 2 to make life easier. There's a bunch of simplifying measures you could have taken, but I'm focusing right now on the procedure itself. All right, so x plus is minus 2 over square root 2 plus square root 50 over square root 2 And x minus is minus 2 over square root 2 minus square root 50 over square root 2. Now is a good time to take out my calculator and punch these in. Minus 2 divided by square root 2 plus square root 50 divided by square root 2. Oh, look, it's equal to 4. And the other one, minus 2 divided by square root 2 minus square root 50 divided by square root 2, and this one's equal to minus 6. There you go. 2 answers. It's helpful to check at this point in time. Okay, so let's move on to the last part of this, a derivation. It's not the case that using the quadratic formula and using complete the squares are two different ways to do it. The quadratic formula is a shortcut that essentially takes the complete the squares procedures and lets you jump to the end. It lets you bypass all this algebra. The algebra is important, and it's helpful for you to practice your algebra. It's a great practice, so I want you to learn how to complete the square, but they're the same thing. And the reason they're the same thing comes from something called a derivation. A derivation is essentially, it is a type of mathematical proof, but essentially what it is a type of formal mathematical algebraic argument that shows where a particular result comes from. Okay? So in this case, the result we're interested in is us saying equals 0 has roots at minus b plus or minus square root b squared minus 4ac over 2a. So one question we can ask is, where did this result come from? How do you know it's true? A derivation is a type of proof that starts with an expression like this and uses algebra until it ends up with this particular expression. And I'd like you to learn the derivation for the quadratic formula that you've been using, and it comes from using complete the square on this expression. So the way it goes is you start with a particular expression and then you work it through algebraic steps until you get this desired result. That's what we mean by a derivation. Let's try this one. ax squared plus bx plus c is equal to 0. ax squared plus bx is equal to minus c. I've moved the c over to the other side. Now I want to complete the square. I want to ask myself, what would I need to put here for this to be a perfect square? Well, my little a is equal to a squared is equal to big A, so little a is equal to square root of a, whatever that is. And so little b is equal to the coefficient of the second term divided by 2 little a, so it's b over 2 square root a. And then I can square that. B squared is equal to big B squared over 4 times A. Okay, so this expression here is what would have to be in there for this expression to be a perfect square. Let's put it in. ax squared plus big BX plus B squared over 4a is equal to b squared over 4a minus c. So now the expression on the right hand side is a perfect square. Let me simplify the expression on the left hand side a little bit. On the left hand side, or I want to simplify the expression on the right hand side. Let's make their denominators match. B squared over 4a. I can't add the c term because the denominators don't match, so I'm going to do that. So this becomes b squared minus 4ac. Does that look familiar to you? It should. Meanwhile, I can rewrite the b squared over 4a. Meanwhile, I can rewrite the polynomial as its factored form. So little a is square root a, and then that's x, and little b is, oh geez, it was b over 2 square root a, all squared, is equal to I can take the square root of both sides of this. Don't forget the plus or minus. Okay. And then this becomes square root a x plus b over 2 square root a is equal to plus or minus square root b squared minus 4ac, all divided by 2 square root a. If things are multiplied together, you can break up their square roots. If they're divided together, you can break up their square roots, just not if they're added or subtracted. Okay, so now I'm going to continue rearranging this algebraically. Square root ax, I'll move the b over 2 term to the right hand side, minus b over 2 square root a, plus or minus b squared minus 4ac over 2 square root a. And now I'm going to divide both sides by square root a. And that, my friends, is where the quadratic formula comes from. All right, so let's do a quick review. Actually, you know what? What does the medicine wheel for this look like? I forgot. Radicals, simplify, perfect square factoring. And the last one was quadratics. Okay, I really want to emphasize all these relationships because what we just went through was a package of different ideas that were all related to each other. Okay, the idea is that there are some quadratics that are perfect squares. Not all the quadratics are perfect squares, but some of them are. And this is important when it comes to radical expressions. Okay? The idea here is that most quadratics can be factored, but perfect squares factor in a really specific way. They factor as one linear term all squared. And that means that when I take the square root of a perfect square, I can simplify it in a way that I can't simplify a general quadratic. Okay? So because of the way perfect squares factor, I'm able to take their square root, and that lets me simplify expressions by taking the square root of a perfect square. And so overall, I'm able to solve general I'm able to solve quadratic equations involving quadratic polynomials equal to some number. I'm allowed to figure out what x is, essentially by rearranging this system and then trying to make it a perfect square. Trying to rearrange it in such a way that the stuff on the left-hand side is a perfect square. I then can take the square root of both sides and solve for x. Okay? Well, this is a procedure that I expect you to be able to do, so please practice it on your own. All you need to do is take a quadratic expression and then rearrange it till you find the answer. Okay, I'll talk to you later.